Hello everyone, I hope you are doing well. My name is Navahuja, and the purpose of my Science Fair journey was to compare and pinpoint certain aspects of an aerodynamic airfoil that achieved maximum efficiency for flight conditions by quantitatively measuring the phenomena on and around four airfoil structures. This data process took place with a set of physical trials and computational fluid dynamic trials, as well to analyze the complex problem of selecting the most efficient airfoil for pressure distribution, CFD trials, lift results, and external aerodynamics. By utilizing the CFD tool and physical trials for aerodynamic results on the four airfoils, we can assess the difference in which the airfoil characteristics have specifically on the performance of the airfoil for in-flight conditions. The setup/data collection methods of the simulation and physical results was completely original. The fields of CFD is just a sector of the simulation world. FEA, or finite element analysis, is where developers get the opportunity to simulate and test structures, static analysis regarding industrial equipment, and dynamic analysis, focusing on automotive vehicles/dynamic response. Even though simulation of potential engineering applications does have its limitations, managing every single parameter, it offers unlimited possibilities into the engineering field on such a powerful computational processors using cloud. And with the world crisis occurring today, it's another reason to use such a powerful tool to test designs and eventually lapping market competition with a much greater amount of innovation. Now, simulation does have its boundaries. Literally, in normal flight, an aircraft is in free flying space. However, in simulation, present are enclosure dimensions, affecting the results. Physical trials aren't necessarily inaccurate, but they are still a very effective way to test designs with adjustments to the potential designs in the physical world, a more quicker and desirable process. Part 2: Data Results and Analysis. An airfoil design optimization had to be taken into place first, given that an airfoil produces a substantial amount of lift for the aircraft, and it is vital for aircraft efficiency in general. By the data collected and analyzed for CFD trials, I was able to state that the external aerodynamics was most effective for the cambered airfoil, attaining most laminarity. The pressure distribution on and around the wing was most effective for the delta wing, given that higher concentrations of pressure in pascals were located on the bottom region of the airfoil than above. The difference in pressure from the leading edge to the trailing edge was minimal, which was a positive sign as well for the airfoil pressure concentrations. From the force plots produced by CAE Cloud Computing Software on SimScale and inputted values/conditions, this data included the lift coefficient, drag coefficient, and moment coefficient. These were the main lines that made up the graphs for the airfoil, and since lift is a primary factor in aerodynamic analysis for this experiment and for aircraft performance, a greater value in lift and greater exponential growth had to be observed in graphs, with conditions remaining constant from each trial. The airfoil producing the most amount of lift from the wing shape based on simulation runs on CFD was the cambered/broader frontal region airfoil, with a sharper and greater curve than the other lift-producing airfoils. This shows that an airfoil with a broader frontal region greatly increases lift generation. The average airfoil was the least efficient airfoil regarding lift generation, because the values were negative for the entire simulation plotting. However, laminarity and external aerodynamics was almost tied with the cambered airfoil, the most laminar flowing air particles. Drag coefficient for the force plots remained low and constant for the simulation one, which represents an efficient airfoil. Recall from the research paper on the CFD and physical trial experimentation process/analysis that moment coefficient is the tendency for rotational motion. During in-flight conditions, rotational motion is highly located at the direct leading edge of the airfoil, or stagnation point, where air particles split and diverge across the airfoil structure. This setting was named for the leading edge for every airfoil, unaffecting results. In physical trials, the average airfoil and the cambered/broader airfoil leading edge was analyzed and compared to other airfoil lift production, and stated that both produced the most quantity of lift with a sharper decrease as well in mass. This was differing from the CFD lift results, in which lift efficiency was negative, signifying the effect of the enclosure dimensions on airfoil outcome. External aerodynamics was viewed, however, camera quality could have affected this flow regime analysis. The delta wing external aerodynamics was viewed as turbulent fluid particle packets. However, it was an expected outcome that a delta wing design produces the turbulent airflow by vortices, therefore producing lift. The experimental process of designing and testing 4 airfoils through CFD was just one possible engineering application. Another design suitable for CFD cloud computing software is testing the structural integrity and durability of an airfoil, optimizing engine efficiency by replacing fan blades with a more effective airfoil shape, or analyzing thermal expansion/change during in-flight conditions on aircraft in the components itself. CFD also allows the capabilities of simulating a real-time city design and locating specific concentrated regions of greenhouse gas emissions, enabling leaders for a change in production rates in those areas. The future of science and technology is simulation. Thank you for listening to my presentation, and I hope you learned a lot about design validation and analysis. Thank you.